Okay, so let's say we had our differential equation in this form. Sorry if I may sound a bit like groggy. I kind of just woke up, so I'm doing this on the spot. But yeah. So let's say we had a function in this form where, as you may know, m of xy here is just a derivative of f with respect to x, and n of xy is just our derivative of f with respect to y. And normally the way we go about these equations in this form is when they're exact, meaning that the partial of m with respect to y has to be equal to the partial of n with respect to x, meaning that they're essentially the same function. So that means this would bring up an exact solution. However, in this case, what if it's not exact? What if we did this process and we find out that these two parts aren't the same? So pretty much how we go about something like that, if that were to happen, is we're going to be using integrating factors, meaning that when we multiply our original function here by some integrating factor u of xy, it suddenly makes this exact. So how can we solve for u of xy that would make this exact? Well, what we could do right now is, by definition of exactness, instead of just having our m here, we would have our integrating factor and our n. So we have the derivative with respect to y of m and u. This is going to be equal to the derivative with respect to x of n and u. So now pretty much we gotta solve this equation to be able to solve for what our integrating factor is. So what we could do here is just do a product rule on both sides. So on the left side, we're gonna get the partial of m partial y, then you leave the u alone, plus partial u partial y times m. Same thing on the right side. So we have partial n partial x u plus, then we have partial of u partial x n. Okay. So now that we're at this point, what we could do is get these u terms on one side and get everything else on the other side. So I'm gonna subtract by this term and this term on both sides. That will leave us with partial of m partial yu minus this. So we get partial of n partial of xu. This is going to be equal to this partial u partial xn. Then we're going to subtract this term right here. So minus partial u partial y of m. Okay, so now at this point what we could do is factor out a u on the left side. So get rid of this and this, putting this on brackets and multiplying it by u. Okay, now at this point, if we want to solve for u, we're going to make a few assumptions on u, because u can be a function of x and y, or of just x, or of just y. But we're going to be going over where u is just a function of x and y, and you'll be able to see how we can solve for u. Okay, so now here we have the cases where u of x, or where our function of u is just a function of x, and our function u is just a function of y. If your integrating factor happens to be a function of u and y, or of x and y, then this would be straight up the equation that you would use to solve for your integrating factor. Just divide both sides by this term, then you can solve for your function of u. But right now, these are special cases where it's just x and y. So let's go over when u is just a function of x first. Notice how if u is just a function of x, this term right here completely goes away, because when you take the derivative with respect to y of a function that's just a function of x, this is just going to be 0. So for u of x, we're going to be left with, sorry about that, we're going to have u times, pretty much the left side just stays the same. So we have this. And it's going to be equal to this part right here. So partial of u, partial of x times n. Okay. And it may not look like it now, but this is a separatable equation. We're going to get the u's on one side and get everything else on the other side. So I'm going to keep this big term, this fat term, on the left side. So we have this. I'm going to multiply both sides by partial x. So we get it right here. I'm going to divide both sides by u. So we get 1 over u right there. I'm going to leave our partial of u. So we have it right here, and divide both sides by n. And at this point, what we could do is just solve for our function of u. So how we do that, we integrate both sides. And our left side, we're just going to leave it as it is. But for our right side, it's going to be ln of our function u. We don't have to worry about a constant because u is a function of x. It's not its own thing. And if we wanted to solve for this, we just have this. We pretty much have e raised to this power along with this right here as well. So if we wanted to solve for an integrating factor that's just a function of x, we would have e raised to the integral of our partial m partial y minus partial of n partial x. And we also have our function n at the bottom. Then right here, instead of writing partial of x, I'm just going to write d of x. This is assuming that once we integrate this, it turns out that it's just going to be a function of x. This is going to be equal to u of x. So here is one case scenario where our integrating factor is just u, where our integrating factor is just a function of x. So now that we have that, we can do the same thing on our, we could go on when u is just a function of y. We can do the same thing. So when we integrate, or when we take the derivative of a function that's just of y with respect to x, this is just going to be 0. So essentially it's kind of the same process. So now we have partial m, everything on the left stays the same. So we have this is equal to the negative partial u partial y of m. And if we were to go ahead and solve this the same way we did with this one, we would get e to the power of the integral of this whole term right here. So we get partial m, or I'm going to take this negative and put it on the inside. So now we get plus and minus. So really, this part right here would be, we have partial of n partial x minus partial m partial y over m dy. And this would be our integrating factor that's only a function of y. So here are the two special case scenarios. Sorry about that. So yeah, here are two special case scenarios when our integrating factor is just a function of x, or integrating factor is just a function of y. And technically this one as well, if our integrating factor is a function of both u and y. And yeah, we could go over some practice problems involving these equations right here, mainly these ones right here. Okay, so here we have a differential equation, And I might have said something wrong in the when I was trying to derive this. If you're looking for an integrating factor that's a function of x and y, you can't really use the equation right away. You would have to multiply this part by x of n times y of n, and basically you would have to solve for the values of n and m. It's basically a bunch of algebra. So that's the case if you want to solve for an integrating factor that is in terms of x and y, but we have equations that would allow us to solve for integrating factors that are just a function of x and y. In this case, for example. So here, basically, we're just going to test for exactness first and make sure that we could use our integrating factors for this problem. So by definition of exactness, this right here should be true. If we took the derivative with respect to y on this side, we get 1. And on this side, if we took the derivative with respect to x here, we would get 2xy minus 1. And as you can see, that does not equal. So this is where we can use our integrating factors. Basically, if we want to use our integrating factors, we got to use both of them. Pretty much we're going to do kind of trial and error. We're going to first use our integrating factor of y. And we're basically going to try seeing if we get only a function of y. So when we integrate it, we should only get a function of y. There should not be an x there. If there is an x, then this would not be an integrating factor. So So we have e to the power of the integral of, okay, sorry about that. It's hard for me to remember these equations off the top of my head, but yeah. So let's just go about this. So we're just pretty much doing plugins. So we have we still have e to the power of. This first part right here, when we take the derivative with respect to x here, we get 2xy minus 1. We also have this minus sign right here. And if we take the derivative with respect to y over here, we just get a 1. And this is going to be all over our m function, which is this. So 3x squared plus y, then we have our dy. And this can turn into, we could get these two ones together, exp. So we would get 2xy minus 2. Then we get 3x squared plus y dy. And as you can see right here, we're not able to get rid of our x term. So our integrating factor is not going to be just a function of y. So now we could go test out to see the integrating factor as just a function of x. So here we have our integrating factor as just a function of x. Again, we're just going to do plugins. We're just going to plug things in. So we have e to the power of the integral. Now, the only thing different we have here, so at the top, we have everything as the same. So this one, the derivative with respect to y is just 1. And actually, I'm going to write it as it is. So this would just be 1 minus, and here we would have the derivative with respect to x. So we would have 2xy minus 1. But in the bottom, we now have our n function. So it would be x squared y minus x d of x. And here we could get these two ones together. So we get negative 2xy plus 2. Yeah, negative 2xy plus 2. Negative 2xy plus 2. And what we could do here at the top is factor out a 2. And same thing with here at the bottom, we can factor out an x. So we have e to the power of the integral of negative 2. Then we have xy When we take out the -2, this is going to be a -1 right there. And then when we factor an x on the bottom, we get x, y, minus 1. As you can see, these cancel out. So now we're just left with an integral that's just in terms of x. So for this problem, our integrating factor is just a function of x. So now we're just left with e to the power of the integral of -2 over x d of x, which then turns into e to the -2 ln of x, and this just turns into x to the -2. So here would be our integrating factor for this particular problem. And now if we want to solve for this, so now we know that our integrating factor is x to the -2. We're just gonna multiply this equation by the integrating factor. So really we get x minus 2 times 3x squared plus y dx, plus then we get x to the -2 of x squared y minus x dy is equal to 0. And now as you can see, this first part right here, this is going to be our new m of xy. And here, this is going to be our new n of x. Sorry about that. So here, this is going to be our new function of n of x, y. If we want to solve for this differential equation, then take note that m of xy is the derivative of the function with respect to x, and this is equal to m of xy, so we could just have x minus 2. Really, when we substitute that in, we get 3 plus yx to the -2, and here we could just integrate with respect to x. So our function of x and y is going to be, we have a 3x, and then doing this we get minus y x to the -1. And then right here we also have a function, some function of y. So I'm going to write f of y. We could take the derivative with respect to y on both sides. So on the left side, we're left with partial of f, partial y. And we take the derivative with respect to y on this side, we get negative x to the -1 plus f prime of y. And as we know, partial f, partial y is just our n of xy, so we could just plug that in. And when we substitute our x to the -2 here, we get y minus x to the -1, sorry. So now we have that. These x terms cancel out, so we're just left with y is equal to f prime of y. So now we could just integrate this. So bam, bam. And now on the left side, we're just left with 1/2 y squared is equal to f of y. So now we could just plug this in on this part right here. So we have f of xy is equal to 3x minus yx to the -1, then plus 1/2 times y squared. And as you may know, this is our level curve, so this could just be any constant, really. So here would be our solution for this differential equation. Sorry. So yeah. So yeah, it's all about the integrating factors really. The only thing new here is really the integrating factors, whether it be a function of x or y. You just gotta test out both of them. Make sure that you only get a function of x and y with, yeah, you just gotta make sure you get only a function of x or y, depending on which one you're doing. And yeah, on to another problem. Okay, so here we have another differential equation. And for this problem, we're just gonna solve for the integrating factor because as soon as you get the integrating factor, you're able to solve for a solution for this differential equation. So yeah, first let's let's just assume u is a function of y. So we have our u of y is gonna be e to the power of this integral. So u to the y is gonna be exp. And it's really just a bunch of plugging in. So we have partial of n over partial of x. This right here would get us 2y plus 1. I'm going to put this minus right here. And then partial m partial y is going to be 4. It's going to be 4y. Yeah, it's going to be 4y plus 2. And then we're just going to put our m function on the bottom. So 2y squared plus 2y plus 4x squared dy. So now that we have that at the top, we could we could just stop right here because this x down here, we're not able to get rid of it. So right away, we know that if we were to integrate this, we just know that we're not gonna get just a function of y because this is pretty much a requirement that this has to be a function of y. So right away, our integrating factor is not a function of y. So now we go on to our integrating factor as a function of x. So again, just plugging things in. So partial m partial of y, that's just going to be our 4y plus 2. Putting our minus right there, and then partial n partial of x. This right here would be 2y plus 1. Okay. And then at the bottom, we have our n function this time. So 2xy plus x d of x. Okay. At the top, what we could do is get everything together. So we have the integral of 4y minus 2y, that's just going to give us 2y. Then 2 minus 1, that's going to give us plus 1. At the bottom, we could factor out an x. So now we have 2y plus 1. And as you can see here, the y's do cancel out. We could get rid of them. They're gone. And then our d of x there. So now the solution for our integrating factor is going to be in terms of x, but it's going to be e to the power of the integral of 1 over x d of x. This will just give us e to the ln of x, which is just x. So our integrating factor for this problem is just x. And we could verify that real quick. So we don't need this y. Our integrating factor is just x. Let's verify that real quick. I'm just gonna have this boxed in. So bam. And if we want to verify that, let's do partial. Really, we're just multiplying everything by x. So let's just do that. So when we multiply everything by x, we get 2y squared x plus 2yx plus 4x cubed. This is going to be dx plus then 2x squared y plus x squared dy. And now we just do the definition of exactness that will verify that there is a solution for this differential equation, or at least an exact solution. So partial m, partial y, or m in this case is now going to be this part right here. So we have partial y of 2 y squared x, basically this, plus, or not plus, then the partial derivative with respect to x of this part right here. This is our new n, pretty much. So 2x squared y plus x squared. On the left side, if we take the derivative with respect to y, we get 4yx plus 2x. And on the right side, if we take the derivative with respect to x, we get this 2 comes down, so we get 4xy plus 2x. And as you can see, they're equal, so there is an exact solution. And yeah, you can pretty much use that integrating factor to figure out the solution to this differential equation. And yeah, hopefully this video helped you guys out. And yeah, see you guys.